Hello everyone, welcome to the channel. This video covers top 10 must-know concepts of artificial intelligence. This is part 2 of the must-know AI concepts. I suggest you to watch part 1 video before watching part 2. I have provided the link for the part 1 video in the description of part 2. Let's get started. Have you heard about transformers? I'm sure you did. The alphabet T in most popular ChatGPT stands for Transformers. GPT stands for Generative Pre-trained Transformers. GPT uses a transformer architecture with a large number of parameters that allow it to learn and generate text. Transformers are used in both machine learning and deep learning neural networks. The concept of transformers is different in machine learning and deep learning. As we saw in part 1 of the video, in machine learning pipeline, the input to machine can be text data, audio data, image data. As machine like computers do not understand this text, audio and image data which are in the form of strings, the data needs to be converted to numbers in matrix form and to vectors. In each stage of this conversion from text to numerical form vectors, the input data is transformed at each stage using transform method. If you have used any machine learning library, then transformer functions may look like tokenizer.transformer in NLP, that is natural language processing. Transform method updates data set and passes data set to the next stage. In machine learning, a transformer is an algorithm which can transform data from one form into another form. Input data frame is transformed to feature vectors using transform method. And then the feature vectors are transformed into output predicted labels using transform method. Transformers ensure clear data processing from model training to model evaluation. Coming to the estimator. An estimator is an algorithm that can learn from training data to create a model that can make predictions or inferences about new data. Estimators have the method estimator.fit to learn from the training set. An estimator with predict method attempts to make predictions on new unseen data based on learned model. For example, classifiers such as linear regression or random forest classifier. An estimator fits on data frame to produce a transformer. Data frame calls a method estimator.fit random forest classifier. And then the transformer method transforms the random forest classifier to random forest model. Therefore, machine learning workflow is a chain of estimators and transformers. Moving on, let us look into transformers in deep learning. Transformers that are used in GPT and large language models LLMs. Transformers convert data from one format to another format where a sequence is input and an output is generated based on the input. Transformers are designed for sequence-to-sequence task. Translate a sentence from German to French or from Hindi to English. Input sentence is in English language and the output sentence is in Hindi language. Transformers understand the entire context of the sentence and process the entire sentence instead of processing word by word. Let's say we have a sentence like, I like pizza, so I ordered it. Here the transformers analyze the complete sentence and understands the word it in, as pizza in the second sentence. I ordered it. These transformer models can understand the sequence by analyzing the entire sentence instead of analyzing word by word, so that the transformer can get the context of the entire sentence. Another example, I like cheesecake, I ate it. Transformer model can understand that the word it in the second sentence is referred to cheesecake in the first sentence. Let's say you are replying to a question, how are you? You frequently reply to the question by typing I am fine. Then as you type I am, the word fine is displayed from auto suggestions to you in the message box. Let us look into another example to understand the capability of transformer model. Let us look at two sentences. First sentence, I am at river bank. Second sentence, I am depositing money at bank. The word bank in the first sentence refers to river bank, that is river where there is water. Bank in the second sentence refers to financial institute. Transformers use self-attention mechanism. Self-attention weighs the importance of each word relative to others. For example, in the sentence I like cheesecake, the first word I relates to second word like, third word cheese and fourth word cake. The next word, that is second word like, relates to third word cheese, fourth word cake and the first word like. Then the next word, that is third word cheese, relates to fourth word cake, first word I and second word like, and so on. Transformer represented as encoder and decoder architectures. Input to encoder are words which are converted to embeddings. Embedding is a large list of numbers representing the different aspects of the word being embedded. The model learns these numbers during training process. In general, transformers consist of encoders and decoders. There are also encoder-only models like BERT, which stands for bidirectional encoder representation from transformers, and decoder-only models like GPT models. The computations required to learn token words representation can be parallelized using graphic processing units (GPUs). This parallel processing makes it possible to use large amount of textual data to learn token representation. This parallel processing reduces model training cost. Now let us look into the most important concept of machine learning, that is activation function. The functions that govern the artificial neurons behavior from one layer to another layer in neural network. If you are new to neural network, then in simple terms, a neural network is a network of neurons. Neurons communicate with each other similar to the neurons in our brain, that is biological neuron. A basic neural network consists of input values and then input layer, then hidden layers and output layer. As the input data moves from input layer to hidden layer to output layer, data is influenced by activation function types. Activation functions can be applied at each stage of hidden layers. which is input to the next layer, or activation function can just be applied on the output layer to produce output values. There are several activation functions. The most popular activation functions are sigmoid, ReLU, that is rectified linear unit, and softmax. Before discussing each of those activation functions, let us understand why we need activation function. When information is fed to the brain tries to classify the information into two categories. Can you guess the two categories? Yes. One is useful information and the second category is not useful information. Not all the information or data is equally important or equally useful. Some of the data is just noise. Activation functions are the functions that help the neural network to process the relevant data points and discard or ignore the irrelevant data points. Activation functions reduce noise data and carries only useful information. Without activation function, neural network would be a simple linear transformation. Activation functions make neural network nonlinear. Activation functions will make the neural network powerful so that the network can learn from the complex patterns from the data. We use the activation functions to propagate the output of one layer node forward to the next layer. Activation functions help to converge laws quickly. For example, when I say apple, what is the first thing that comes to your mind? Apple fruit or software company Apple? If it is apple fruit that comes to your mind, then apple in red color or apple in green color. Mostly it would be apple in red color because our brain has given more weightage to the apple fruit in red color. In this case, the most relevant data would be apple fruit in red color and less relevant data would be apple fruit in green color or the software company Apple. But it also depends on the context. If we are discussing about the software companies, then we would think of Apple Software Company first. In all other contexts, including when we are hungry, it would be apple fruit. If a neural network does not have neurons, then every neuron will only be performing a linear transformation on the inputs using the weights and bias. Although linear transformations make the neural network simpler, but this neural network would be less powerful and will not be able to learn the complex patterns from the data. Now coming to the types of activation functions. The most popular activation functions are sigmoid, ReLU, and softmax, and also tanh. Sigmoid activation functions reduces outliers in the data without removing them. Infinity values are converted to range between 0 and 1. Sigmoid value is clipped between 0 and 1. Next, rectified linear unit. A ReLU unit clips each value less than 0 to 0. If the value is minus 5, then the value is reset to 0 as minus 5 is less than 0. If the value is 5, then ReLU does not clip the value because 5 is greater than 0. And ReLU value clips the max value between 0 and the value. If value is less than 0, then make it 0, else value remains as it is. This ReLU activation function can be combined with dropout regulation techniques which we saw in part 1 of the video. Now coming to the softmax activation function. This clips the negative values between 0 and 1. Output probabilities always sum to 1 in softmax. There are other activation functions like tanh, which deals with negative numbers in the range of -1 to 1. If value is less than -1, then set the value to -1. If value is greater than 1, then set the value to 1. So tanh value ranges between -1 and 1, including -1 and 1. Now, how to choose the right activation function? It depends on the problem. We have to choose activation function for quick convergence of the network. Sigmoid used in binary classification like mail spam or email not spam. Sigmoid activation function may give a probability that an email is spam by 90%. Sigmoid has single probability for neurons. Softmax is used in multi-class classification where there are multiple probabilities for neuron and the sum of all the probabilities is 1. In multi-class like image classification with multiple objects, only one class is correct. Let's say an image classifier has images of dog, cat, car, cycle. Out of these four, only one classification or one object is correct. ReLU is used in CNN networks. We'll discuss more about this neural networks like CNN, RNN in the video that will be posted next month. Next interesting topic is loss function. Loss functions calculate how close a given neural network is ideal. Loss is difference in predicted output versus actual output. Loss assigns a numerical score to the neural network's output given the true expected output. Loss can occur at several stages of machine learning pipeline or at several stages of neural network. Loss could be due to weight and bias, state of neural network, feature engineering, or due to some configurable parameters. In simple terms, loss function boils down the difference between the desired output and the predicted output. What are loss functions? Now let us see where are loss functions used. Loss functions are used on output layer to find the difference between the predicted output versus actual output. Loss functions are also used during feature engineering process. Remember the feature engineering concept from part 1 of the video? Could you recollect what feature engineering is? In simple terms, feature engineering converts input data like audio, video, and image data, which is in string form, to numbers or numerical form. Some widely used loss functions are hinge loss, root RMS, entropy loss functions. In hinge loss, if there is no difference between the desired output and the predicted output, then loss is zero. Otherwise, loss is linear. In root mean square error, which is used in regression, error is predicted as squared and is averaged over the number of data points. This is similar to the uh, root mean square RMS formula which we use in mathematics. Next, cross entropy is popular loss function used in classification problems. Product of probabilities are transformed into sum of the log of probabilities. Log function is used in cross entropy. Cross entropy is also called negative log likelihood, maximizing the probability. This is also used in multi-class classification. Now, The word loss function in machine learning is same as error function, cost function. Loss, error, cost functions all are same terms in machine learning. Hinge loss is used in classification like head or tail, or used to calculate loss in classification like no fraud is 0 and if it is fraud it is 1. RMS is most widely used loss function. This is used when we want to consider the outliers. When making investment in stock market or when buying an insurance policy, we want to consider outliers. So RMS function is used in such applications. Cross entropy is used in multi-class classification like dog, cat, car in image classification. Cross entropy is of two kinds, binary cross entropy and categorical cross entropy. Don't get confused between hinge loss and binary cross entropy as both the losses are used for classification, that is 0 and 1. But the differences in hinge loss is used in supervised learning like SVM, that is support vectors, and the range is -1 to 1, and this is less sensitive to outliers, whereas binary cross entropy is used in linear regression and neural network where the range is between 0 and 1 and more sensitive to outliers. Cross entropy penalizes correct prediction if the prediction is out close to 1. The next two slides will discuss about gradient descents. In part 1 of the video, we learned basics of gradient descent, GD. GD is an optimization algorithm which adjusts parameters such as weights to reduce error. We can also say that GD as a pathfinding algorithms in machine learning. Let's understand GD with an analogy. GD is like a route map showing different directions to your destination. That is long route, short route, route with traffic and route without traffic, and short route with potholes, and you choose the route which is safe and which takes less time to travel to reach your destination. Once you choose the shortest route and continue to travel, at some point the short route may branch out to some more routes to your destination, and then again you choose the shortest route from those branch out routes and repeat the process till you reach your destination. Here you are eliminating other routes as and when the route map shows the directions, and you are choosing the safe route at each point that takes less time to travel to reach your destination. Here less travel time is less error. In simple terms, gradient descent GD is the process of measuring loss and changing the weights by one step in the direction of minimum error or loss. The steps of adjusting the weights to minimize the error is repeated until the point where we have maximum likelihood or great accuracy and minimum loss. The algorithm moves downhill slope towards the lowest loss. Then what is the problem with GD? Problem with GD is when the above repeated steps of measuring loss and changing the weights are applied to large data set. The process of calculating the minimum error becomes slow. So for large data sets, stochastic gradient descent, that is SGD, is used. SGD slope is calculated based on batch instances rather than at end. In SGD, compute the slope and update the parameters after every training sample. This speeds up learning rate. The advantage of SGD is faster learning rate, and smooth convergence as gradient is computed at each step, hence lowest cost per parameter update. But the drawback is it may introduce some noise. Now let us look into gradient descent and vanishing and exploding gradients. One of the reasons for gradients to vanish and explode is due to the output of activation functions like sigmoid, which are applied on the first few layers of the neural network. Due to vanishing gradients, the loss values are very small or negligible, so the network stops learning or network learns slowly. How to prevent gradients from shrinking or vanishing? Use activation functions like rectified linear unit or LSTMs, long short TMs, and then gating mechanisms like GRU. Exploding gradient, as the name suggests, gradient becomes too large. The issue is the loss function values become large for training data and the parameters like weight may become large, damaging the learned features in the model. Then what is the solution to the exploding gradient? Tripping the gradients if the loss value exceeds a given threshold. The next 4 slides are about evaluating the AI models. As we saw in part 1 of the video, confusion matrix is the tool which is used to evaluate AI models. For details on confusion matrix, please watch the part 1 of the video and the link for part 1 is provided in this video description. Now using this confusion matrix tool, we'll measure model accuracy, precision and recall, sensitivity and specificity, and F1 score. Confusion matrix gives insights into how correct our predictions were and how much they are different from the actual value. What is input to the confusion matrix? Input to the confusion matrix is predicted values and actual values, which are labels. The matrix can be drawn in two ways: predictions in column and actuals in row, or actuals in column and predictions in row. Cell values in the matrix change accordingly. Let's take an example of an email classification as spam and not spam. Let's assume we have 10 emails and we have to classify them as spam and not spam. In that, let's say 3 emails are spam and 7 emails are not spam. Now, first row, first column, true positives. These are the data points classified as the positive by the model, and the data points are actually positive. This is a simple cell and easy to understand. Email is correctly classified as spam. So the result is 3 emails are spam out of 10 emails. Then comes false negative. Label is positive. AI model classifies data points as negative, but the data points are actually positive, which is incorrect classification. In this, 3 emails are actually classified as spam by the model, but they are not spam in reality. Then comes false positive. Label is negative. In this, the data points are classified as positive by AI model, but the data points are actually negative. In this, out of 10 emails, 2 emails are classified as not spam, but they are spam. True negative samples. In this, data points are labeled as negative, which are actually negative. Email is correctly classified as not spam. 7 emails are not spam out of 10 emails. True positive correctly classified as class of interest. So it is a perfect model. False negative incorrectly classified as not the class of interest. This is a very bad model or a dangerous model. False positive correctly classified as not class of interest. This is okay model. True negative incorrectly classified as class of interest. This is good model or perfect model. Let us understand why the model is perfect and not perfect in the cells with an example. Let's say we have developed an AI model in healthcare to predict if the patient have cancer disease or not. A perfect model that is true positive predicted that the patient has a cancer disease, and the model also predicted that the patient has cancer disease. Next, why the model in false negative is called dangerous or very bad model. In this, the patient actually has cancer disease, but the AI model has predicted that the patient doesn't have cancer disease. If this model is considered, that the patient may not take the treatment for cancer, so the error in this model has to be fixed. This is also known as type 2 errors. Next, in the second row, first column, false positive, label negative. This is okay model because patient doesn't have cancer disease, which is a good news, but the model predicted that the patient has cancer. So the errors in the model type 1 errors has to be fixed. Second row, second column. Patients actually don't have cancer, and model also predicted that the patient doesn't have cancer. So this is also a perfect model as the model predictions are in line with the patient's health status. Now let us define model accuracy. Model accuracy is the degree of closeness of measurements of actual output to the predicted output. If the actual output and the predicted output are same, then AI model is fully accurate. If the actual output and the predicted output differ by n, then n is the difference between the actual and the predicted output. Generally, accuracy is measured in terms of nines. That is, a model with 99.99% accuracy is a good model. Then comes how do we measure accuracy of a model? Accuracy of a model is sum of true positives and true negatives divided by total samples, that is true positive to true negative, false positive and false negative. Next, let us move on to precision and recall. Precision is defined as closeness between the estimates based on the different samples under the same conditions. The portion of the data points that AI model says are relevant are actually relevant. Precision is calculated by true positives divided by sum of true positives and false positives. That is, for example, precision is equal to heart patients correctly identified divided by sum of heart patients correctly identified and individually incorrectly labeled as heart patients. Then what is recall? Recall is how often positive predictions are captured or identifies all relevant instances, that is completeness of quality. Recall is also called as hit rate. AI model finds all data points of interest in a data set. Recall is calculated as true positive divided by sum of true positives and false negative. That is, heart patients correctly identified divided by heart patients correctly identified plus individually incorrectly labeled as not heart patients. Let us understand precision and recall with the same healthcare AI model developed to identify cancer disease. We want to find all patients who actually have the cancer disease. In this case, we can accept a low precision if the cost of the follow-up examination is not high. What is low precision? Low precision means the algorithm returned less relevant results. In this cancer disease example, patients do not actually have cancer are also listed along with the cancer patients. In such scenarios, there is no harm in follow-up medical examination of the patient for cancer disease if the cost of the performing medical test is low. What if the cost of the medical test is high? If the cost of the medical test is high, then low precision issues has to be fixed. We can accept low precision when the medical cost of follow-up is low. It's like giving a heads up. When the follow-up medical examination cost is high, then we may not be able to afford the cost. So find the exact number of patients who need follow-up examination by high precision. Low precision occurs when very few of your positive predictions are true. Low recall occurs when most of the positive values are never predicted. Precision expresses the proportion of the data points our model says was relevant were actually relevant. Recall can be thought of as a model's ability to find all the data points of interest in the dataset. As precision increases, recall decreases, and vice versa. To achieve right balance between To achieve right balance of precision and recall, machine learning algorithms should try to minimize the number of true positives while minimizing the number of false negatives and false positives. Now let us move on to the next topic. Simple topic: sensitivity and specificity. Sensitivity means as recall this sensitivity same as recall, also known as true positive rate. Sensitivity quantifies how well the model avoids false negatives. Model would be 100% sensitive if the model detects all people with cancer disease who need medical checkup, that is follow-ups. Specificity quantifies how well the model avoids false positive. Specificity is specific, identifies healthy people with no symptoms of cancer. Use sensitivity to avoid missing out on serious test results. Use specificity for confirming test results. Sensitivity and recall are same. Recall term is used in machine learning. Sensitivity term is used in statistics. You can compare the formula of sensitivity in this slide with the recall formula in the previous slide. When to use sensitivity and when to use specificity. It depends on the problem statement and cost of training, like the cost of follow-up on medical tests or the cost of missing a diagnosis and performing entire test again. Now coming to the last topic of this video, F1 score or F1 measure. In case we want to find an optimal blend of precision and recall, we can combine the two metrics using what is called F1 score or F1 measure. F1 score is harmonic mean of both precision and recall. F1 score is used as an overall score on how well a model is performing or how well a model retrieves relevant results. F1 score is harmonic mean, that is 2 multiplied by precision and recall by sum of precision and recall. And what is precision and recall we have already seen in the previous slides. This brings us to the end of this video. I hope you liked this video. See you in the next video. Until then, please subscribe to the channel and let me know your comments. Thank you for watching.